I'm Rohit, the TA for this course, Nuclear and Particle Physics, and this is the third live session. And the course tutor is Dr. P. Paulos from IIT Guwahati, and we are having this live session where we will discuss some example problems and maybe recap some of the concepts. So, like to follow these live sessions, you should, you should go through the lectures of, the corresponding week. So, today we will discuss some concepts and problems from week three, where the lectures are mainly on radioactive decay and alpha decay and some concepts of shell model. I think is also there in the first lecture. So so let's start. So last time we were having some confusion regarding one problem where we had to calculate the excited state for I think neon. Sorry. Does anyone remember this problem that we are having? Actually, yeah. So yeah, thanks. So yeah, we had some confusion regarding which excited state. Uh, I mean this the unpaired neutron will go to. So let's write this down again. Let's write down the states again, and we will see. So we have one is half, one p 3/2, then one p half, and then we have one d 5/2. Then we have 2s 1/2, and then again we have 1d 3/2. I think this is sufficient for us. So as we have number of protons, we have 10, number of neutrons we have 11. So this is inert, so proton will not dictate anything for this nucleus. So number of neutrons is 11. So one of the neutron is unpaired. So that will dictate the uh, spin and parity of this nucleus. So let's fill these states with the number of neutrons. So 2 will go here, then 4 will go here. So we have 6. Then 2 will go here, 8, and then the rest of the 3 will go here. Okay. Now the question is, in the excited state, what could happen? So what are the possibilities? Okay. So suppose one of the neutrons from here can go to the S half state, or maybe it will go further to 3/2 D 3/2 states. Or what can happen is one of the neutron from P half state can go to, you know, uh, S half state. So all these possibilities always are there, okay, and it depends on the energy number. Energy that is provided to the nucleus. I mean, if it has sufficient energy, it will acquire higher states and all kinds of. So this is basically, we cannot say for sure what will be the what states we will observe. It's an experimental problem. So if you do, I mean, what you do is you go and measure, you do basically nuclear spectroscopy, or there are other methods, and then you see that what kind of excited states are there for this nucleus, and from there you make a conclusion that, yeah, which excited states are there. So these kind of possibilities are always there, okay, given the amount of energy that is available. So I hope, I mean, this is also discussed in the lectures for some other nucleus. So I was just, recapping. So anyone has any problem here, or it's fine? Okay. If everyone is okay, then let's move to today's problems. So yeah, I'll go through the problems, and if anything, like, uh, I'll discuss the concepts along with it. Okay, uh, so don't worry. Let's. I mean, and I want you guys to also answer and interact with me. So just, I mean, you can ask anything if you're not uh, understanding anything. Okay, so uh, just, don't be quiet. Just keep. You can ask in the chat, or you can just directly unmute and ask. So okay, so let's start with this problem. So the question is, which of the following statements are correct regarding the low-lying excited states of uh, titanium nucleus? Okay, so again we have sorry, number of protons 22, so it's inert, and neutrons we have 23. So again, this will dictate what will happen to the nucleus. I mean, the properties of the nucleus. so let's write the states again, like we did here. So again, one is half, one p 3 by 2, one p half, one d 5 by 2, 2s half, then 1d 3 by 2, and let's write some more. We might need 7 by 2, or 2p 3 by 2, and 1f 5 by 2. Okay, so that's enough, I think. So these are the states available. So let's start filling this up. 2 goes here, 4 goes here, 2 here, 6 goes here, then 2 goes here, 4 goes here. We have 3 more, right? This is the magic number, 20 here ends. 3 goes here. Okay, so this is the ground state. Now, so what about the excited states? Okay, now what can happen is one of the neutron can go here, so that will give us uh, 3 by 2 spin. But so after here we have 2p half, right? Sorry. Which is very unlikely for a neutron to jump to, two states and go to half. So I mean, this option is obviously wrong. Okay, this one is also wrong. Spin half is not expected. So this one seems correct. But what about this? So we have an option to go to, 5 by 2 also, right? So is 3 by 2 more probable than 5 by 2, or what do you guys think? Please answer. Hello?
Be
Uh,
very big.
yeah, sorry. Can you repeat? I was.
So the 3 by 2 seems more probable because
Yeah, yeah,
the gap
because
between the
because it needs
first
more energy for 5 by 2, right?
yes, right.
Yeah. So then D is also correct. So both options are C and D are correct here, right? Spin half is, very far. So it had it. I mean, it can go here, but it needs a lot of energy. And if you give that amount of energy, then what happened is that maybe something weird can happen. Like one of the neutron from here can go here, or something like that will happen, instead of one neutron going to, such a high state. So so that's why spin half is not expected. Okay. Okay. So anyone has any doubt here? Okay, if not, let's go to the next problem. So here we have a problem on radioactive decay. Okay. So the question is, certain nucleus X1 undergoes radioactive decay to produce X2, and which in turn decays to X3. So this is a problem of chain decay. Okay. And the decay constants are lambda 1 and lambda 2. Fine. Now, in a short time, so that lambda 1 t and lambda 2 t are very small, so lambda 1 t and lambda 2 t are less than maybe 1. as compared to 1. The number of x2 in the sample are related to the number of x1 at time t equal to 0. So we have to find n2, okay, as a function of, so n2 in terms of n0, okay, we have to find. N2 is the number of x2, okay, and n0 is the number of x1 at time t0, okay. We don't have to bother about x3 in this problem, right? Now, how to solve this? So, in the lectures, you might have seen this case. So here, so at time any time t, the number of x1 which is given by n1 is simply given by n naught exponential minus lambda t, right? This is the standard, radioactivity decay formula. And then the rate of, the rate of whatever you can say, like uh, eh, the rate of change of number of x2 as is given by this formula. So minus lambda 2 n2. Now, why we have two term here? Because here x1 is going to x2 and then x2 is decaying further. So for the decay we have this thing, and because we have here constantly x2 is getting produced from x1, due to that we have this term, okay. So this you should understand why there are two terms here. If there had not been an x1 which is decaying into x2, then we would have simply this thing, right? But since there is a x1 which is feeding into x2 via radioactive decay, so that's why we have this term, the first term. Is that clear? And okay, thank you. And if you solve this simple differential equation, you will find uh, this expression. So I think this is solved in the lectures. You can go and check, and if you don't understand, then let me know. I'll solve it again here in the next tutorial. So this comes out to be in terms of number of x1 at time t is equal to 0, this comes out to be uh, this value, this expression, okay, lambda 2t. Yeah, okay. So now I mean, this is basically the expression that we have, but we can further reduce it because there are some condition given, like lambda 1 t and lambda 2 t are very small compared to 1. So let's use that, and let's write this again, and we can do a expansion of uh, this these terms, exponential terms, I mean a series expansion. So you know that exponential can be expanded into a series, some series. Uh, so e to the power minus lambda 1 t can be written as 1 minus lambda 1 t plus lambda 2 t, lambda square t square by 2, and then there are other terms. You know this, right? Everyone knows about this series expansion of exponential. Okay, so let me write the general expression. So if you have an exponential like this, it can be expanded as 1 plus x square by 2 factorial plus x cube by 2 by 3 factorial, and like this. Okay, so that's what I have used here. But since taking a cube here doesn't matter, because it's given that we are looking at a very short time. So t to the power cube will give you a very small number. So anyway, we are ignoring that. Okay, and then we will have another one for the second term, which is 1 minus lambda 2t and plus lambda 2 square t square by 2. Okay, so let's simplify this further. Okay. Hmm. By the way, I think I think since time is very small, so order of 2 will also don't contribute here. So let's put these also to 0. Okay, and then uh, 1 1 gets cancelled, 1 minus 1 0. So what we are left with is lambda 2t minus lambda 1t. Okay, and we can take t common, so then there will lambda 2 minus lambda 1, and there is 1 in the denominator which get cancelled, so we get lambda 1 and not t. So interestingly, you see that uh, for a very short time, okay, the number of x2, the number of x2 sample which is there, uh, it depends only on the lambda 1. Okay, it doesn't depend on the lambda 2. I mean the decay constant, I mean it's decay constant. It depends on the decay constant of the previous sample, like x1, from where it is getting created for a very short time, in a for a short time t. So this is very interesting. Okay, uh, so yeah, just to keep in mind, like
So T short time, as in T should be lesser than the mean lifetime of the second daughter nucleus.
Yeah,
Oh,
yeah, yeah. Basically, yeah. Because yeah, I mean it should be very short. Yeah, because if given enough time, what will happen is this X2 will also be start decaying depending on its lifetime or half time. So then that lambda 2 will also start contributing. But as long as the time is very short, like it's written here compared to 1, it should be very small. Then in that case, so that you can ignore this term, this t square term, as long as you are able to ignore this t square term, okay, you will get this expression which depends only on lambda 1. Okay, otherwise this lambda 2 will always be there. So it's a matter of time. I mean, at what time, till what time it's negligible. uh, so yeah. So any other question here? Did you understand, Adnan?
yes, sir. Yes, sir. Yes, sir. Got
Okay. Yeah, it's just matter of time. Okay, let's go to the next problem then. So it's again a similar kind of problem, but now the third. No, we will concern with our you know third sample in the chain. So yeah, let's uh, let's read the question. A radioactive element X decays into Y, which in turn decays into a stable element Z. Okay, and the decay constant here is lambda 1 from X to Y, from Y to Z it's lambda 2. And if there are again n0 atoms of X at short time, again we are giving the condition that uh, lambda 1 t and lambda 2 t are small compared to 1. Okay, at short time the number of atoms of Z will be, okay. So we have to find n3. Okay, and let's write it uh, n n2. Yeah, so I don't know if you guys are familiar with the formula for n3, but I will write it here. So again you will I mean, to get this, to get the formula for n3, you have to just solve another differential equation, which is dn3 by dt equal to lambda n uh, lambda n 2 or 3, lambda n2, right? Lambda 2 n2, sorry. So the expression for n2 is here, okay, and so you have to just solve another differential equation, and then you can get the expression for n3. So this, I mean, this derivation is little involved. Uh, I don't know if I should try to solve it in the. I mean, I don't know if you guys in the lectures. I don't know if it is done, but you can find the derivation in any standard book, or if you are not able to find or understand, then let me know in the next session, then maybe I'll try to derive it. Okay, so right now I'll just write the, so yeah, from this differential equation, minus lambda 2 into, actually it will be positive, it will be positive because it is getting created, it is not decaying. Okay, created from n2, so the rate will be positive. And the expression for n3 comes out to be this. So you notice here that N3 does not depend on the intermediate stage N2. Okay, it directly depends on only the uh, number of x at time t is equal to 0. So this is interesting. Okay, I mean obviously because we have two differential equation, and here solving the first one gave us n2 which depends on only n0, and then when you solve the third one you will put n2 there, so obviously this intermediate one goes away. So you finally get expression for n3 which only depends on n0, and obviously on lambda 1 and lambda 2. Okay, so just to keep in mind this thing. So yeah, again we can simplify this expression. So let's I mean using these condition, so let's try to do that. But from the options you see that we have two options with t square terms and two options with only uh, t terms. Okay, order of 1, I mean 2 to the power 1. So let's try to simplify this, and we will, I mean, act accordingly that like which one to keep. Okay, so yeah, let's I mean again we can ignore the uh, third order terms obviously, so let's keep it to the second order term and let's see what happens. Okay, so yeah, n3 is equal to first let's get these things out. So lambda 1, lambda 2 minus lambda, I mean I'm just multiplying the this term into the both terms and while expanding this uh, term. Okay, so here we'll have 1 minus 1 minus lambda 1 t plus lambda 1 square t square by 2. Okay, let's not take the third order terms. Okay, it's fine. And use the big bracket here. So, and then we have the negative sign, the multiplication by lambda 1, lambda 2 and not lambda 2. So yeah, I mean, you guys can also try on your own, or you follow the follow my solution, so that I don't, if I make any mistakes, please let me know. And then multiplied by 1 minus 1 minus lambda 2t plus lambda 2 square t square by 2. Okay, so okay, now okay, let's simplify this. So 1 will cancel out here in both terms, and we will be left with what? uh, two terms, right? So wait, this is lambda 1, right? So first let's cancel lambda 1 here, lambda 2 here, okay, and multiply lambda 2 inside. So basically, what on the outside we have only this thing remaining, and in the inside we multiplying lambda 2 here, so minus lambda 1 lambda 2 t plus lambda 2 lambda 1 square t square by 2. Okay, and then here we'll have a naught lambda 2 minus lambda 1. And inside we will have,
Sir, should the signs be plus plus lambda 1 lambda 2 t minus lambda 2 lambda 1 square t square?
oh yeah, 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 sorry, thank you for noticing. Yeah, yeah, and here also we have lambda 1 lambda 2 t minus lambda 2 square t square by 2. Okay, sorry, lambda 1 multiplied. So far so good. Now you will see that these terms get cancelled, right? So what we are left with is uh, so we are basically taking this term common, so we have minus lambda 2 lambda 1 square t square by 2 minus minus plus lambda 1 lambda 2 square t square by 2. Fine. And then we can take out lambda 1 lambda 2 t square by 2, right? So that we will get lambda 2 minus lambda 1 in the numerator and lambda 2 minus lambda 1 in the denominator get cancelled, and we have lambda 1 lambda 2 n naught t square by 2. So here you see that, so this is n3. Okay, so yeah, here you see that number of jet which is getting produced as a function of time, it it depends on t square. I mean, it depends on uh, second order in time. Okay, and for a very short time, this value will be very low. Okay, and it will increase. I mean, it's not a linear dependence on time. With time it will, increase quadratically. So it will go like this. So in for a short time the number will be very low, but as time progresses, the number will increase, uh, quadratically. So yeah, again this is very interesting.
So here, unlike the previous question, why did we consider the second order of time? If you're taking very short time spans, then shouldn't we neglect the t square as well?
Yeah, I mean, if we could, I mean, we if you neglect it, so then it will be just zero, right? I mean, you can neglect it here also, like put it zero. For a very short time it will be zero. I mean, it's just to show that for a, like lowest order what you get in time, so it's t square that comes up. Okay, I mean, you can put it to zero, like for the very short time it will be obviously closer to zero, the number of n3. But I mean, we just wanted to know what dependence on time it will have. Okay, for the for a short time, obviously, and as time increases, you will get higher order terms here coming in. But I mean, whatever will happen, the dependence on t will not be there. I mean, there won't be any term because this gets cancelled every time, right? So you will have either t square, then you will have t cube, or and such like that. So it will never be a linear dependence like we had in the last case.
Good, sir.
Yeah. So that is interesting to see. Okay. So anyone has any other question? If not, let's move to the next problem. So this is a problem on alpha decay. We have polonium 211 going to lead 207 plus alpha particle. And mass of polonium is given, which is 21098 blah 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 0. Mass of lead, mass of lead is given, which is 206.97 U in unit of U. So you know that 1 U is equal to 931.5 MeV, right? So because the answers are in MeV and GeV, so eventually we'll have to convert it. And then mass of alpha particle is 4.0026 U. Okay, and we have to find the kinetic energy of alpha particle. So how to do that?
So we have a formula.
Yeah, I mean we have a formula. So okay, so let me write the formula. The formula is something like this. This is, I mean, just the ratio of alpha particle and decayed daughter. Okay, and this is the Q value of the reaction. What is Q value? So Q value of a reaction is, yeah, anyone want to say?
Basically, the total energy of both the daughter and the alpha particle.
Yeah, so that comes out to be in terms of mass difference, that will be just mass of polonium minus mass of lead and subtracted by mass of alpha particle, right? Into C square to convert it into the terms of energy. And so the masses are given here, and to like so but to fit into this equation you have to convert them into MeV. So you just multiply all the three by 931.5, you get a value in MeV. Okay, and uh, then you subtract the polonium. I mean, you subtract the mass of lead and alpha from polonium, and you get the Q value, and you put the Q value here. You put the mass of alpha particle, which is given here 4, and the mass of here you don't need to convert it into MeV, it's just the ratio. So you put in the units of U. Okay, and then you can calculate, you can do a simple calculation of kinetic energy of alpha particle. So should we go through this problem, or should I leave it for you guys to try? I mean, I can solve it. I'll have to also use the calculator. All the steps are here, so uh, it's just a matter of time. I mean, it will take some time. So but anyone want to guess what could be the answer? Obviously, it will be some definite answer, not, you know, can be any value like this.
So B, sir, I guess.
7.59 MeV. Hmm.
Because A and C are giving in giga electron volts, which is, I
Yeah.
think,
Oh, sorry. Yeah, this is in giga electron. Oh, sorry. Yeah. Yeah. Then obviously it will be in MeV. Yeah. Hmm. Yep. It will be in MeV. Giga. I mean, GeV is too much. If you have alpha particle in GeV energies, then it's a problem, right? So yeah, obviously B will be the answer. So yeah, you can try it out. This will be the answer, I guess. So anyone wants me to solve it? Okay, if not, then thank you. But yeah, you can try. Uh, this will be the answer that you will get. Okay, let's go to the next problem then. Uh, I mean, it's the similar kind of problem regarding alpha decay. So here Q value of uh, alpha decay from of uranium to thorium is given. Okay, so uranium 234 going to thorium alpha particle. The Q value is 4.8587 MeV. Okay, and again the mass of helium and uranium is given, and we have to find the mass of thorium. Okay, in atomic masses units U. So how to do that? It's simple, right?
yes, sir, again, the formula only, the first Q formula.
Yeah. So uh, yeah, I mean, so first the Q value you can find Mu minus M thorium minus M alpha, right? Don't you don't need the, so Q value is given, yeah, in MeV. So you again convert these masses into MeV, because these are given in the units of atomic masses. So I'll just write out. So this will be 234.04 into 931.5 MeV minus uh, mass of the thorium that we have to calculate, and then for alpha particle it's 4.00260 into 931.5 MeV. So now this will this if you do this calculation, this will comes in the terms of MeV. Okay, and then you have to convert it back into atomic mass unit. So you'll just divide by 931.5. Okay.
So instead, we could just take 931.5 common from all three, send it on the left side, and then we'll get the thing in U only directly.
Yeah, that is also. I mean, you'll just divide here and keep these things in atomic mass unit. Yeah, that is also fine. Anyway, that you want to try. So yeah, this is also a simple problem. Just you have to use the Q value of the reaction. Okay, this is a simple one. I hope everyone can solve it. Okay, so let's go to the next problem then. So now this is uh, this is also a simple problem again regarding alpha particle, but it's a different kind of. So instead of radioactive decay of alpha particle of some nucleus via alpha decay, what we are having here is what should be the minimum energy of photon for it to split an alpha particle at rest into a tritium and a proton. Okay, so so basically you have a alpha particle, okay, and you bombard it with a photon gamma, and this splits it into uh, tritium, which is 1,3, and a proton. Okay, so how to solve this? Any idea?
Sir, so the energy of the photon should be equal to the Q factor of the splitting, right?
Energy of the photon, right?
Yeah,
Yeah,
it should be equal to or greater than the Q value for the splitting.
yeah. Minimum it should be equal. Yeah, obviously. Uh, but okay, so the alpha particle is at rest, right? So and it is for it to split into a yeah, okay. So we can write it like that, like this. So energy of you know the photon plus uh, mass of alpha particle should be equal to mass of uh, sorry tritium, I mean, plus mass of proton. Is it fine? I mean this should so
So subtraction should be happening, right? Like from the alpha particle, we're getting two things.
mhm.
So the energy needs that much energy needs to be removed. Oh no, okay, okay.
Yeah, uh, yeah, that is, but this, yeah, that is true. But this is the this should be fine, right? Some energy, we are providing some energy, okay, and this energy plus uh, whatever the mass of the alpha particle is, right? It these two creates these two at rest. So minimum energy means that whatever we are creating is should be at rest. We are not giving any kinetic energy to it. Okay. So that is the minimum energy that we need from photon. So
So if
that,
we consider the Q factor as well, that is also only the mass difference. It does not we are not considering the kinetic energy of the particles. Because if it's at
yeah,
rest,
yeah,
then
yeah,
we'll
yeah.
keep
I mean,
taking.
you can write in terms of Q factor, but see, Q factor comes for a radioactive decay. Okay. I mean, we consider Q factor for a radioactive decay, not for a process like this. So this is, we are splitting a nucleus. So I don't know if Q factor, um, because Q factor, what is the definition of Q factor? It is the total energy of the, uh, decayed particles, right? Kinetic energy of the decayed particles, and that comes out to be the mass difference of the uh, radio, I mean, of the decayed products and the decaying nucleus, right? But here such things are not there, so that's why I'm not writing the Q value here. Okay, but this should work, right? Energy from the photon and the mass of alpha particle, these two combines and creates these two, right? It's just energy conservation, nothing else. Or in terms of, mass energy conservation, whatever you want to say. Yeah, it's basically energy conservation. It's fine.
Yes, sir. Makes sense, sir.
Yeah, so then gamma will be just mass of tritium plus hydrogen minus mass of alpha particle, and the masses are given in atomic mass unit in the problem, so we will just multiply by 931.5 MeV. Okay, and if you will solve it, you will get I think closer to 19.3 MeV. Okay. Yeah.
So with 938, we have to multiply, right?
Oh yeah, it is AMU. Yeah, for AMU, it is 938. Yeah, you're right. 938 maybe. Yeah. Sorry. Yeah. For you, it is 931.5 maybe. Yeah. Yeah, it is given here. So, yeah, this is also nice problem, but it is little different. It's nothing to do with radioactive, I mean, alpha decay. Just, I mean, you can split any nucleus by providing energy in form of bombarding some particle onto it like photon or neutron or anything. I mean, nuclear physics experiments always do this. So yeah, this is a nice problem. Okay, let's then go to another problem. So here the question is, if in a spontaneous alpha decay of uranium at rest, the total energy released in the reaction is Q, then the energy carried by the alpha particle is. So, so we have provided Q for a decay of alpha decay of uranium. So it again might go to thorium, but and we have to find the energy carried by alpha, so basically the kinetic energy. Okay, so I don't know if you guys I mean, if this was discussed in the lecture. So if if the mass of alpha particle is very less than the mass of daughter nucleus, so the formula becomes so it's like this. So the formula becomes a minus 4 by 4 q. Are you familiar with this?
Yes, sir. Sir derived an equation in the
Yeah,
in the lecture.
and a is the simply the A is the atomic mass of the uranium. I mean the decaying nucleus. Okay. So A here is U, which you know that uranium has mass of 232 or something. Yeah. So we can calculate it. So the numerator will be 2. Sorry. Numerator will be 228 divided by 232 q, which will be then 57 by 58. So this was a simple problem just to remind of you of this equation. So you don't always have to apply, where did it go? You don't always have to use this one. Because here then you need to know the mass of the daughter nucleus. So if the mass of uh, if the mass of the decaying nucleus is order of like 100 greater than alpha particle, then this formula works fine. This formula might not work for a lighter nuclei, but anyway lighter nuclei doesn't do radioactive decay in general. So I think this formula applies for all the radioactive, I mean for all the alpha decaying nucleus. So yeah, this is a nice formula. Okay, then let's move to the next problem. Uh, so the question is, the half-life of a radioactive nuclear source is 9 days. So T half is given 9 days, and the question is the fraction of nuclei which are left undecayed after 3 days is. So at t equal to 3 days, we have to find fraction of undecayed nuclei. Okay, so what fraction of nuclei that is remaining? So first of all, I mean, looking at the option, can you guess what fraction will remain after 3 days if t half is 9 days? So first is 7 by 8, right?
So B,
D,
B or D?
1/3. So I mean, one third seems to be very, straightforward, but you've seen that the equations for nuclear, I mean, radioactive decay is not linear, and it depends on, yeah, I mean, it goes as exponential.
So D then it makes sense,
Yeah,
right?
I mean, let's see. So okay, what is the formula that we have? So radioactive decay, we have this formula, right? Number of nucleus as a function of time, I mean, which is there as a function of time, and so if we divide n0, I mean, n naught is the number of nucleus initially at t equal to 0. So then this is the fraction that we want to calculate, right? Fraction of nucleus that is remaining, right?
So here we can take T as T half by 3.
Yeah. So yeah, we have this formula, right? Lambda equal to ln2 by t half. Do you know about it?
Yes, sir.
Yeah. So then we can put it here. So minus ln2 into t by t half, right? And t half is 9 days, t is 3. So let's put everything. So you will get ln2 by 3, right? And then it's just, manipulation. So to get negative sign removed from here, you can invert 2, right? And 1 by 3 you can take here like this, right? And then exponential of natural log is, I mean, it cancels, so you are left with this thing. Is it fine? Everyone got it? So what I did is, so I had by 3, right? So first, you guys know that e to the power minus x is equal to e to the power 1 by x, right? Yeah, and then also e to the power 2x is sorry what I'm writing, not e, I'm talking about log, sorry. Yeah, ln minus ln x is equal to ln 1 by x, and if you have something like this, then it's x square. So I've used these two here, uh, and I got this. Okay, so I hope it's clear. So yeah, D is the correct answer, rightly guessed by Adnan. Okay, so then let's move to the next problem. So yeah, this is a problem on beta decay. I don't know if oh wait, sorry, sorry. Let me switch my iPad again. Something happened. Okay, so yeah, let's read the problem. So tritium, the isotope, 3 hydrogen. So in tritium we have 1 proton and 2 neutron. Uh, you know, you know that. And then it undergoes a beta decay. Okay, so it doesn't matter if you have not studied beta decay. It's just a kind of radioactive decay in which electron or positron get produced. So and T half is given. So beta decaying, and T half is 12.5 years. So this problem is little involved, so I'll go through it slowly. Okay, T half is given 12.5 years. Then question says is that an enriched sample of hydrogen gas containing 0.1 gram of tritium. So we have 0.1 gram of tritium. Okay, and it produces 21 calories of heat per hour. Okay, so via this decay, it produces this energy per hour. Okay, so for these data, we have to calculate the average energy of beta particles emitted. So, I mean, this energy is being carried out by the beta particles. Okay. So, so we have to calculate the average energy of beta particles. Okay, that is the question. But okay, so let's go through it slowly. So first, I mean, since it is a radioactive decay, so this formula is always valid, right? this formula is always valid. Now, uh, now let's first find out lambda. So lambda is by t half, right? If you calculate it, so t half is 20.5. So I'll calculate it in number of hours. So 365 into 24. Let's not consider leap year for now. So we will get, you will get this number. Okay. So we have lambda. Now, uh, now we have to calculate this n. Any idea? Uh, so because if we calculate number of, you know, number of tritiums that are there at a certain time t, okay, which is given here, so 0.1 gram of tritium. So then we can calculate the rate of decay, and 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 it's just a matter of time. I mean it's just a matter of, you know, conversion. So we will know the number of decays per hour, right? And then we can calculate the average energy based on this number. Okay. Sorry. Yeah, this is fine. So we have to calculate the this number. So any idea? No, this number. I mean n. So any idea how to do that?
So we solve the differential equation.
No, because we want to find the rate, right?
So we can we use the n naught n is equals to n naught e power
N
minus.
naught e to the power minus lambda t. You want to use?
Can we use that for beta decay?
So yeah, this, I mean, obviously it comes from here, so we can use this. But the thing is,
So I think n naught we can get from I think if we have the gram,
yeah.
I think we know the tritium
But then,
molecular mass.
but it is redundant, right? You want to know the rate, but it comes as a function of time, right?
Yes, we don't have time.
Yeah, so I mean, so this n, uh, so if we consider like, yeah, the thing
Can we
here,
take 1 hour as our time, sir? But
no,
like calorie.
that will not help, because I mean it's given here is that it, the sample, which contains 0.1 gram of tritium, produces 21 calories of heat per hour. Okay. So what is given here is this thing. So what is given here is dN by dt. Okay. And uh, uh, Sorry,
So
no, this is
dn
not
by
given. This we have to find. But no, what I'm saying is, uh, if we consider our at any time t, like this number of tritium atoms are there, okay, so that will be our n, won't it be?
yes, so are we, do we have to use dn by dt, but like as the main this thing? Because the heat being produced is by dn by dt, right?
No, heat being produced is dn by dt into, number of yeah, in heat being carried by each beta particle, right?
Yes, sir.
So, but we don't know that how much heat each beta particle is carrying out, right? But what we know is this number, like this number of tritium at tritium is producing 21 calories of heat per hour, okay. So if we calculate this, like what is the rate of what is the rate of decay of tritium, if we calculate this, right, so that will be the same thing, uh, at which at the rate, I mean that rate will be the same at which the beta particles is are emitting, right?
Yes,
Rate
sir.
is same, I mean this isotope is decaying and beta particles are getting emitted.
Yes, sir.
Yeah, so we can simply, dn by dt, we can simply write. So okay, first of all, so how many atoms, sorry, how many number of uh, atoms of tritium will be there in 0.1 gram of tritium. So we know the molar concept, right? So we know that so because the atomic mass, I mean atomic weight of tritium is 3 gram, so 3 gram will have 1 mole, right? And 1 mole of this tritium will contain 6.023 into 10 to the power 23 atoms, right? So 0.1 gram will contain 6.03 into 10 to the power 23 by 3 uh, into 0.1. This number of tritium atoms will be there, right? So dn by dt will be then simply uh, this number into the lambda that we calculated, 6.33 into 10 to the power minus 16, okay, per hour. So this whole thing is per hour. So this is the rate at which the nucleus is decaying, okay. And uh, now the average energy that we want to find. So okay, this if you calculate, it comes out to be 1.27 into 10 to the power minus 15 decays per hour. Okay, and the average energy will be, so uh, per hour what we are getting from this sample, it is 21 calories, right? So this divided by the number of decays per hour, which is 1.27 into 10 to the power minus into 10 to the power 70. So this will be the average energy of beta particles. I mean, this will be the average energy that is getting produced when tritium decays into beta particles, basically. Because, so yeah, so this is the 21 calories per hour. So per hour get cancelled, and you get, so this is 21. So here you have hour inverse, and here you have also hour inverse, and this is calorie. So you get the unit of energy anyway, and you can convert calorie into joule by multiplying it with uh, 4.18. So this will give you joule, and you can further multiply it with 1 point, no, to get into kV or MeV, you have to divide by 1.6 into 10 to the power minus 19, because 1 electron volt is this much joule. So this you can do. So
So we again have to find for the beta particles, right?
no, so this is the big, so that so so this is the average energy of the beta particles, right? Because I mean it's nowhere written that, so the question is little confusing. Okay, it's nowhere written that this 21 calories of heat that is being emitted, it is because of the tritium, going into beta particles, beta decay. So beta particles are taking these heat out of the system. Okay.
So, but the daughter nucleus also has some energy, right?
uh, in case of beta decay, daughter nucleus has very, I mean, like 99 or some percent of energy the beta particles take away. It's so yeah, daughter particles don't get much of the energy from beta decay. So I mean, yeah, it is not exact value. Obviously, there will be some energy shared with daughter particle also. But yeah, the maximum energy will be carried out by the beta particles. So yeah, I mean, think about it, and I think it will be convincing once you think about it. Also, the beta decay is not discussed in week 3, right? Maybe it will be discussed in next week. Or...
It's there for week 4, sir. In week 3 we had till alpha.
Yeah, yeah,
But
yeah, yeah. Yeah, I should have kept this for the next week, but it's okay. I mean, I thought it's nothing. I mean, there is nothing uh, involved much about beta decay in this problem, so that's why I kept it. So It's just you have to just find out, number of tritium uh, that is decaying per hour, and that we did from here. And we know that 21 calories of heat uh, per hour is emitting. So average energy of beta particles will be just this number divided by the number of decays that are happening. So yeah, I mean, one confusion, I understand this, why we are taking this number as n instead of n naught. So because we are not, see, we at any time t, uh, we can consider our, so we can consider this 0.1 gram of tritium for any time t, right? And since we are not concerned with, uh, we are just concerned with the rate of the decay, so we can use that number in this formula. So that's what we have done. If you want to calculate a number of, number of tritium at a later time t, then you can use this number as n naught, and then you have to know the lambda and uh, the time that you want to calculate. So then you can put it and you can calculate again n. But this n is for you to decide, like, according to the problem, that what you want to do. Okay, do you want to calculate number of tritium at a later time, or you just want to calculate the rate of decay? So if you want to calculate the rate of decay, you can just use this number, right? No one is stopping you.
Yes, sir.
Yeah.
Yes, sir. Yes, sir. Yes, sir.
So yeah, that is the last problem for today. And if you guys have any other doubts or any other question, please let me know. So if not, then let's close today's session, and let's meet next Saturday, same time, 4 p.m. and we will discuss more. So yeah, I mean, uh, I please let me know if you couldn't understand anything. There is a discussion forum, I guess, for this course, and you can write there also if you have any confusion, and one of us will try to address that. So okay, so let's end the session here. Thank you for joining. Bye.
Thank you, sir. Bye, sir.